Hello, my name is Rob Reynolds, and welcome to Calculus, Section 2.1. Today we're going to look at the idea of limits. And it may seem at first that the idea of instantaneous velocity has no relationship to the line tangent to the curve. But we're going to explore how velocity and the tangent line are really the derivatives, what we'll come to know as the derivative. So the first thing we're going to look at is average velocity. And average velocity is really just the slope of the line. And the best way to describe slope of a line is y minus y, change in y, over change in x. So we have a function here, and to find the average velocity between 1 and 3 seconds, we'll actually evaluate the function. The function is not f, it's s, so s at 3 minus s at 1 all over 3 minus 1. And if you evaluate that on a calculator, by plugging the 3 in, you'll get 144 minus 80 all over 2, which is around 32 feet per second. And you could repeat this process for part B. And in part B, it's between 1 and 2 seconds. So again, I change it to f at x minus f of a because this is the general equation that we've always used. In fact, if you look at section 1.1, this is the definition that we were using. You might not have known why we were using it, but we are. But again, s at 2 minus s at 1 all over 2 minus 1 is 128 minus 80 all over 1, which is about 48 feet per second. Again, you could go to Blackboard to see the worked out solutions. Here's a graphic representation of the secant line, and the secant line is really just the slope of the line between 2 points. And as those 2 points get closer and closer, we're getting closer and closer to instantaneous velocity, which leads us to the next example 2. And it says estimate. And when I estimate, notice I just keep getting closer and closer and closer and closer, or the 2 points get really infinitely close. So let's just grab the close point, like something really close to 1, because we want to evaluate it instantaneously at 1. So a number really close to 1 is 1.0001 minus s at 1 all over 1.0001 minus 1, which is 80.0064. Check that on your calculators. Make sure you can get these values. And notice that that's getting very close to about 64. This is approaching the idea of limits, which we're going to get into in this chapter. Notice I'm getting infinitely close to the instantaneous velocity at 1. And again, these notes are posted on Blackboard. There's another way that we could do this. We could have just plugged in the function, which, by the way, you will learn in this chapter, but not in this section. There's the function. Here is s at 1. We evaluated that at 80. And then we could have factored and canceled. And again, we're pushing this to the limit. So after 1 second, the ball is about 80 feet in the air and has a velocity of 60 feet per second. And the way that I got the 80 was evaluating the function at 1. Or finding the y value, basically. Here's my x, here's my y, and remember, y is s at t, or in this case, I let time be 1 second. So that y value should be 80. Again, check that out. So if I push the secant line to the limit, I'll get the tangent line, which is instantaneous velocity. Average velocity is the secant line. Instantaneous is the tangent line. In this example, we have a parabola, and it says explain why the slopes have 0 for any of these values which have symmetry, of course. So if you were to quickly draw this, a and f of a is over here for this point, and this point would be negative a, f of a, and you can see the slope here is going to be 0. But we could do it algebraically as well. The slope of the secant, again, 2 points. Average velocity would be f of negative a minus f of a all over negative a minus a, which is 0 over negative 2a, which is slope 0. And then the tangent line, well, the tangent would be down here. It only crosses once. And that would be pushing the limit when these 2 points just get infinitely close, like there's no distance, instantaneous velocity, there's no distance between the 2 points, then that would be slope 0 as well. You can try that. Here are some more examples. I'll jump to C and you can finish up some of them, but s at 2 minus s at 1 all over 2 minus 1 would be 192 minus 112. You can check this on your calc and then see it. So, but one that I do want to make sure that you can do, which will be on most any assessment, would be making sure that you could evaluate these variables. So on letter D, it would be s of 1 plus h minus s at 1 all over 1 plus h minus 1. Oops, I put the parentheses in the wrong spot, so sorry. Minus 1, 1 plus h minus 1. And then evaluating this function at 1 plus h means go to this function and plug in 1 plus h every time you see a t. So negative 16, 1 plus h quantity squared plus 128, 1 plus h minus 112. That's the function evaluated at 1. All divided by h. And this is just going to be in general form, so I'll try to get it down in terms of h. But if they ask for instantaneous velocity, I would take the limit and just push it to the limit. But I don't think there's a limit here. Remember this, I would do that square double square rule. So negative 16 h squared minus 32h plus 128h. Check my math and see if that doesn't all combine down. Factor out an h and cancel it. And what should be left is the negative 16h plus 96. So again, I skipped some steps. You can go to Blackboard, check out to make sure that the mathematics is correct. I wanted to show you a couple things on your calculator as well. If you want to evaluate several points, the fastest way to do it is on your calculator. So go to your y equals and type in the function, but instead of t, I've typed in the x. And I'm going to ask for a table setup, but let's hit second window and actually change our auto to an ask. And that way I can ask for certain values. And then so if I hit second graph, I can ask the value. Well, the first value that I want is actually a 2 followed by a 1. And the reason why is because I'm going to do the average velocity. And the average velocity is s at 2 minus s at 1 all over 2 minus 1. Well, you can see from your calculator, s at 2 is 192 and s at 1 is 112. That is handy. Saves a lot of time. So 192 minus 112 all over 1, and that gives me an 80 for the average velocity here. Then I would repeat that process. All I have to do is type in the 1.5 because I already have the 1. So now I would take 156 minus the 112, all divided by 0.5. Come up with that average velocity, which I think is around 88. You can do the mathematics. I'll jump all the way to the end, and I'm going to check the 1.001, which is, now you would think that that's 112.1, but I would actually highlight that in black and don't round. Otherwise, My Math Lab will count your answers wrong because you did take 112.1 and it's not 112.1. It's 112.095984, and I would grab all those, or at least a lot of them. Let's grab it. So it's 112.095984 minus the 112 over 0.001. and that gets 95.984, which is approximately, it seems like I'm cheating because I just told you don't round, but that's about 96. You can see it's approaching 96 feet per second. So you might be, I don't know what my math lab has, but if they wanted you to be really accurate to several decimal places, that's not quite 96, but you can see if I keep pushing this closer and closer, it'll eventually, instantaneous velocity is going to be 96, but this is close to instantaneous velocity. So, oh, good. So, there might be looking for the 95.984. For the last example, if I don't give you a chart, you just have to come up with your own chart. The first thing they just say is go ahead and graph the function, so we can get a visual of what this is. So you can type this function in, and Zoom 6 will give you a standard 10 by 10 screen. And you might want to zoom around, but this looks like a pretty good image of it. You can even calculate the vertex, which I think is at 2, -1. My second calculate, guess left, guess right, guess on. So for part A, a quick little graph reveals I've got a function that looks something like this. The reason why we wanted to find the vertex is because it's very helpful in identifying the point f at which the function has a slope of 0. Well, the slope of 0 is right here. See, this slope is not 0. This is a positive slope in blue, and this trying to find a different color. This would be a negative slope in purple. So you can see that this is steeper slope and it's getting closer and closer. But then when it hits red, there's the slope of 0. And at what point does that happen at? Well, that happens at x equals 2. And they say, well, confirm your answer by making a table. So what's our answer? What are we going to confirm? Well, we want to confirm that the slope is 0 at when the function approaches 2. So let's get close to 2. It's like an interval of 2 and, I don't care, 2.1 might be the first interval. Then the next interval would be like 2 and then even closer, like 2.01. Again, I'm making up these values, so you can make up whatever you'd like. 2.2.001. See, I just keep getting closer and closer to 2.0001. And then again, you go to your calculator, make sure you hit the ask. I want to be asking, well, 2, yay, 2.1, 2.01, 2.001, and 2.0001. And again, don't you think that this might be a -1, but I would actually use this -0.9999 and this one 0.9999. So don't. It's really important. You must, in order to get the right answers in my math lab, you've got to highlight that y sub 1 in black. If you use the number in this column, then you will get a wrong answer in my math lab. So work through that. I think if you set up this table, the slopes turn out to be like 0.1, 0.01, 0.001, and 0.0001, which you can see really close to approaching the exact instantaneous velocity of 0. So again, these are going to be posted on Blackboard, so it appears to be 0. If you have any questions, feel free to email me. I hope this was helpful. Thanks.